Hey there, Calc kids, this is Mr. Bean. Let's get into our second lesson on related rates and learn how to actually solve them today. So we've already learned how to set things up, which is what this very first problem is. We have a relationship here set up with some variables, and now we're going to take the derivative and then figure out how to actually solve those rates that are related to each other, the related rates. So first step here, let's go y squared. So the derivative with respect to time. So that means we're going to have a dy dt. And then this equals 12x cubed dx dt, right? Because again, we're doing this with the derivative with respect to time. And then what else here? We're going to do plus 6, and then the derivative of x is just dx dt. All right, what are we looking for? We're looking for the dy dt, which is this right here. That's what we're trying to find. So we just need to plug in what we know. So x equals 1. dx dt equals 2, but we don't know what y is. So in this situation, when we don't have enough information, what you have to think about is how to solve and figure out what y equals. So you take the original equation, which was just y squared equals 3x to the fourth. Well, we know that x is a 1. Plus 6x, and again we know that x is a 1. So you plug in the values that you know, and then we can figure out, so y squared equals 3 plus 6 is going to be 9, and so then y would equal plus or minus 3, but, I know this is kind of weird, when we're doing related rates, the rates of change and these variables x and y, they always represent something. So you're going to know if it's a positive or negative. So you have to look at the context of the problem to know if it's a plus or a minus. So if for these problems where there is no context, we're just going to say that it's y equals 3, okay, to save us the headache of figuring out if it's both. So that means that we have here, so now this actually just becomes a plug and chug problem. You're just substituting in numbers and quantities and then solve for what you don't know. So the y is a 3, and then the dy dt is what we are looking for from the original problem up here, find dy dt. And then 12 times 1 cubed, so that's just going to be 12. dx dt, do we know what that one is? Yeah, dx dt is a 2. And then plus 6 times 2. So then we have 6 dy dt equals 24 plus 12 is 36. So then our answer is that dy dt is equal to 6. Boom, that's how we find dy dt. Okay, that is what we're doing today. We're going to set up our equations, take the derivative with respect to time, and then plug in all the quantities we know and solve for the one we don't. Here I've given you a bit of an outline of some guidelines to help you solve related rate problems. So the first thing is, I would recommend that you always try to draw a picture. Understand what's happening for the situation so you can start labeling different dimensions and quantities. Then we make a list of all the known and unknown rates and quantities. So let's think about this. Number 1, we've already did that one. We did draw a picture from our last lesson. Number 2 is new. We haven't done this yet, so that one's going to be new. Number 3, relate the variables in an equation. We did that one, right? We did that one in our last lesson. We did number 1, we did number 2. Differentiate with respect to time. We did that one in our last lesson. And then the last thing is substitute the known quantities and rates and then solve. So number 2 and 5 are actually the only new things to this lesson compared to our last lesson. Now here's an important thing. Substituting a non-constant quantity before you take the derivative is not allowed. What does that mean? It means when you have something that's changing, like you know how sometimes we'll have an airplane flying in the sky and that airplane's altitude is a constant, like maybe it's 10,000 feet high, and that's a constant altitude that it's maintaining. You can plug that in before you take the derivative because it's a constant. But if it's a non-constant, do not plug it into your equation, the equation that you came up with in number 3, until after you take the derivative. Okay, you'll see what I mean here. Let's do some examples. We have here a rectangle. Let's draw a picture. Rectangle, I have my width, I have my length. And then we're going to start making, what does it say here? Make a list of all known and unknown rates and quantities. Let's start making a list. The width of the rectangle is increasing at a rate. So that's a derivative. It's a rate of change. So we're going to say that the width, dw dt, the rate of change of width, is going to be increasing, which means it's a positive 2. I don't need to write centimeters per second. I can leave that part off. Okay, we'll come back to the units when we get to the very end of solving the problem. Now, what about a length? Length is increasing at a rate of, so the rate portion tells me that it's dl dt. So I'm just making a list of all of the things they give us. So that's going to be 3 centimeters per second. At what rate is the area of the rectangle increasing? So here's the question. We want to know what's the rate of the area. So I'm going to write down dA dt and say that's my question mark. And then I'm going to put a circle around it. Now, the reason I'm telling you to do this is because you want to keep track of the things that you know and the things you don't know. And this is the big question. Once we know dA dt, we have solved the problem. That's what we're trying to do for this problem. Okay, so at what rate is the area of the rectangle increasing? When its width is 4, so that's another thing we can write down. W equals 4. I don't even know if you have enough room on your practice. You might have to make it over here or something. And then length equals 5. So here's all of our known things. All right, what's the next thing we do? So we've made a list of all known rates, quantities, relate the variables in an equation. That's the easy part because we know this. This is just a rectangle and its area. Easy. Area equals length times width. So there's our equation. We did that part. Now let's take the derivative with respect to time. So derivative of A is just dA dt equals. This is one of the more common spots where kids go wrong. This step right here. Because this is product rule. I have two variables that are being multiplied. I must use product rule. Don't just go straight to dL dt, dW dt. That's wrong. It is the derivative of the first, which is dL dt, and then the second one left alone. Plus, now I leave the first one alone, which is just an L, and then I have the derivative of the second one, which is the derivative of width with respect to time. And now I start plugging things in. So dA dt I don't know. That's what I'm trying to figure out. So I'll just leave that as dA dt equals dL dt substitution here. That's a 3. My W is at 4 centimeters. The length is going to be at 5 centimeters. And the rate of change of the width at this point is 2 centimeters per second. All right, so the answer now. The rate at which the area is changing is 12 plus 10, 22, and let's get our units correct. Centimeters squared, because it's area, right? The derivative of area, so area is centimeters squared per second. Okay, another common mistake would be if kids were to put seconds squared, right? This is not seconds squared, it's centimeters squared. So you have to think about what, if you did second squared, that'd be like the second derivative. Centimeters squared tells you that it's area. All right, so that is a great example of what we're doing today. You're trying to set up a situation, list all the things that you know, create an equation, and then plug in the stuff you know. So let's just do one more example of this. So I'm giving you some easier examples, so you will have a couple ones that are a bit more challenging than this on the practice, though. Let's see here. So we did this one in our last lesson, but we didn't have all of these known units. So I'm going to call this X. So the speeding car is X distance away from the intersection. The police car, I'll call it Y for the up and down. And then this one can just be Z. All right, make a list. What do we know? When the police car is 0.6 miles north. All right, so at the moment when Y equals 0.6. North of the intersection, the car, I should have said the speeding car. So the speeding car, the guy who's trying to get away, is 0.8 miles. So I'll call that X. X is 0.8 miles. So at that moment, the police determine with a radar gun that the distance between them and the car is increasing at 20. So this Z right here is changing at a speed of 20 miles per hour. That is dZ dt. So dZ dt equals 20 miles per hour. I can just say 20. If the police car is moving at 60, so this police car is going towards the intersection at 60 miles per hour, so I can call that the rate of change of Y. So dy dt equals, now what's what I'm doing here? I'm saying negative 60. Why am I saying negative? Because this distance y is getting smaller and smaller and smaller, which means the rate is actually a negative. And we want to know what's the speed of the car. So what we're really looking for is dx dt. That's my question mark. I'm going to put a circle around it just to remind myself that's what I'm trying to find. Okay, let's set stuff up here. So the Pythagorean Theorem will let us relate all of these variables. X squared plus y squared equals z squared. Let's differentiate with respect to time. I get 2x, and none of these are constants, right? X, y, and z. These are all changing as the two cars are moving. So I can't just have a 0 as a rate of change. So I won't have to deal with the constant. So dx dt plus, and then I have 2y dy dt equals 2z dz dt. Okay, let's plug stuff in that we know. 2 x is 0.8. dx dt is what we don't know. That's my question. Okay, perfect. So I'm just going to write out dx dt. That's what I'm going to solve for. Plus 2 times, what's my y? My y is 0.6 miles, so 0.6. And then dy dt was negative 60. Negative 60. And then that equals 2 times, and now my z is, oh, I don't know what z is. All right, so again, this is a situation where we don't have all of the information, so we're going to have to go back a step and figure out z. Well, you can use this x squared plus y squared plus z squared by just saying 0.8 squared plus 0.6 squared, so 0.6 squared, and then that will equal z squared. And when you solve this all out, it's going to give you 1. It's okay to use your calculator on this. You could do that. So z is going to equal 1, so now I know z is 1. And then dz dt, do we know that? Yeah, that's the distance with the radar gun that they checked. So that was 20 miles per hour, that distance there. And now, again, this is just plug and chug. We substitute all the numbers in. You work this whole thing out and solve it. 1.6 dx dt minus, because the negative there, this is 72. I'm using a calculator in the background, okay? I'm actually not that good. And then this is 40, okay. And then when you solve this, I'm gonna go straight to the answer. dx dt will equal, add 72, divide by the 1.6, and you end up with 70. And it's 70, what are my units? 70 miles per hour. So that's how fast the car is going at that exact moment when the police car is 0.6 miles from the intersection and he's already 0.8 miles getting away that direction, okay? So that is my answer for this. Okay, so on this packet, you're gonna have some ones that are a little bit easier like this with just a couple dimensions that you have to figure out, and there'll be a few that are a little bit more challenging. So just make sure you understand it's the same principle every time. Draw yourself a picture, label, set up your equation, label everything that you know, make a big list of all the quantities, and plug and chug after you take the derivative. Okay, rock that mastery check, and I'll see you back in the next lesson.